As someone who used to research quantum physics, it always annoys me so much when Schrödinger's cat is brought up in pop culture. That's because it's interpreted completely wrong. Usually the interpretation is that you may or may not have murdered this cat, and because the box is closed and you don't know what happened, therefore both things must have happened. And they say it's like if you got a letter from your dream university accepting or rejecting you, then until you open the letter, you don't know which, and therefore you're accepted and rejected at the same time. This is completely wrong. The case of this letter is just about ignorance. You don't know which happened, but one of them really did happen. And when you open the letter, you find out the truth. On the other hand, with Schrödinger's cat, there is no actual answer until you open the box. And that actually is a different circumstance. And it's even possible to prove that something different was happening inside of the box even while you weren't looking. So I'm actually going to do an experiment in this video to try and convince you of this fact. Schrödinger's cat really is dead and alive at the same time. The original setup of Schrödinger's cat is that there is a radioactive atom that may or may not decay in that time period, giving off some radiation, and then there's a machine that will detect that radiation. And if it detects the radiation, then it will kill a cat. Now, the whole point of this, the reason why it's interesting, is because this atom is a quantum system. And we know that there is this thing called quantum superposition. When a quantum system like this has two options available to it, so like decayed and not decayed, then it will actually do both at the same time. This is a superposition of these two possible states. Is superposition just the same thing as saying that it is decayed or it's not decayed, but we don't know which, just like with our university letter? Or is quantum superposition really different from just this state or that state, but we don't know which? Well, the maths of quantum mechanics really does say that this state is different from the state that's that or that, but we don't know which. And it even shows us what experiments we can do to prove that this is a different state than just the state of ignorance. But the context for this whole Schrödinger's cat experiment was that Schrödinger thought this was absurd. So Schrödinger, even though he was one of the first architects of quantum mechanics, came to loathe it. Same as Einstein, who was also incredibly important in the history of quantum mechanics. He came up with the idea of a quanta of energy, but afterwards he came to regret it. And he also felt that quantum mechanics just couldn't be true. And it was during one of these correspondences between Schrödinger and Einstein that the Schrödinger's cat thought experiment was first thought up. Schrödinger was trying to point out that quantum superpositions cannot be real. And his argument was this: we have an instrument that measures whether this atom is decayed or not, and if it is decayed, will then kill a cat. Then what happens to the state of the cat? The cat is dead when the atom is decayed, and alive when the atom is not decayed. So because the atom is in a superposition of both states, the cat must be also. So in other words, Schrödinger was pointing out that if small things like quantum systems can be in superposition, which people were sort of begrudgingly okay with, then he was pointing out that even very big things that feel actually real to us, like a cat, could also be in superposition. That's the point of Schrödinger's cat. He was trying to point out that that would be absurd. And so we must reject the idea that an atom even can be in a true superposition of two things at the same time. But let's see an experiment that shows that Schrödinger was wrong. All right, so our version of this experiment is not going to involve radioactively decaying atoms because that would be absurdly dangerous and also needlessly complicated. Instead, there's a quantum system that's capable of going into a superposition that you can actually see with your eyes. And it's just light. We're going to use light to show that a superposition of two different quantum states really is different from just not knowing which one of the two states it's in. Well, first, what are the states that this light can be in? The first is actually called horizontally polarized light. You can see that I've put a filter on this light, which means that all of the light that comes out will be aligned in this direction. And here's what I mean by that. I turn this on and I take another filter that's facing the same way, and then I put it in front of the light. You can see it does nothing at all. And that's because this light is in the same state that this filter will allow through. On the other hand, if I twist this filter around, you can see it pretty much cuts out all of the light. So the difference here is that none of the light gets cut out, and then this one cuts out all of the light. That's because if I'd instead put the light like this, then this filter would let it all through. And now if I twist this, it cuts out pretty much all of the light. So what this suggests is that there's two types of light. There's the type of light where this is horizontal, and there's the type of light where this is vertical. You might protest, though, that obviously there are other states of light, like this and this are not the only two options. What about everything in between? So why don't we check out one of those? So we'll put the light at 45 degrees here. That's roughly 45 degrees. Now I'm going to do the same two measurements as before. And what do you think is going to happen? Let's see. So this cuts out about half of the light. And if I instead twist it around, that cuts out about the other half. The point of this demonstration is to show that when it comes to this measurement, there's two types of light. There's the type of light that's aligned with the filter when it's like this, and then there's the type of light that's aligned with the filter when it's like this. So in quantum mechanics, we would say that this light is a superposition of horizontal and vertical light at the same time. But there is a different and perhaps tempting interpretation for this situation. Instead of believing, like quantum mechanics for some reason, that this light is truly both horizontal and vertical at the same time, why don't we just believe that there's lots of light coming from this laser, and half of it is pointing up and half of it is pointing down? That seems like it would explain our results perfectly, right? Because if we put in the filter this way, then it will block out everything that's not aligned in this direction. So it will take out this, this, and this, leaving behind only the horizontal light, which is about half of it. And if we instead put the filter in this way, then it would block out all the light that's not aligned this way. So it would block out this, 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 and this, leaving only the stuff that's aligned this way, which is about half of it. So this much simpler explanation seems to explain quantum mechanics just as well. Why say that these two things are happening at the same time when it's easier to just say, actually, we just have a lot of light coming out and half of it is one type and the other half is the other type, and you don't know which one it's going to be until you do the measurement. That's a lot more similar to how we interpret a letter like this, right? This letter is going to go out to many, many people, and half of them, or maybe less, will be an acceptance, and half or more will be a rejection. And until we open the letter, we don't know exactly what type we personally got. So shouldn't we treat the light in the same way? This explanation just doesn't seem to make that much sense, whereas this explanation with ignorance seems to make a lot more sense and is a lot simpler. So why does quantum mechanics insist on this one? The reason is because there is one experiment that you can do that will have quite different results in these two cases. To prove it to you, we're first going to consider the case where we have random light that's either up or to the side. And then we're going to consider the superposition, and we'll see how both of them make different predictions. All right, so for now, let's assume that this 45-degree light really is half of the time up and half of the time to the side. And let's consider both of those two cases separately. So first, we'll consider this case. I'm going to twist the light around. So now we know that all of this light is vertically polarized. And if we put our filter in horizontally, it basically cuts out all of the light, which is also what we would expect. But here is the magic experiment that's going to be very different. Instead of horizontal or vertical, why don't I twist my measurement to be 45 degrees? What do you expect to happen in that case? Well, what we find is that about 50% of the light is cut out. That's probably not terribly surprising, but let's just note it down. So the result when all of your light is vertical is that about 50% of it will go through when the filter is at 45 degrees. All right, now let's do the experiment when, in fact, all of the light is horizontal instead. And again, we're going to put this filter in at 45 degrees, and hopefully you can see that about half of the light gets cut out. Again, not super surprising, but we'll write it down. So what have we found? We found that about 50% of the light goes through if all of the light is vertical versus 50% of the light if all of the light is horizontal. So if we have this 45-degree light, and we assume that it is a 50-50 mix of both of these types of light, then what do we expect will happen when we do this experiment? Well, logic would dictate that because it's either one of these two things, the probability that the light goes through is 50%. But you're about to see that that isn't going to be the result. Now, for a second, let's think about how quantum mechanics sees this. In quantum mechanics, the state truly is vertical and horizontal at the same time. And in quantum mechanics, that is quite a different state than having either vertical or horizontal. Even though when you just do a horizontal or a vertical measurement, the results are the same in these two scenarios, they don't need to be the same when you do any other type of measurement. And that is where we're going to see a difference between these two theories. In quantum mechanics, this state, when measured at 45 degrees, will go through with 100% certainty. And this result is called interference. So interference is when there is a difference between the sort of this superposition state versus the sort of ignorant state. And let's see which one is correct. So we're either expecting a 50% drop in brightness or essentially no drop in brightness. Let's see. That was really good. I hope you can see that, but there is basically no change whatsoever to the brightness, which suggests that quantum mechanics is right. Superposition truly is different from just not knowing which one it is. So where does that leave Schrodinger's cat? How can I translate all of this back into that language? Well, in Schrodinger's cat, the atom state is both decayed and not decayed at the same time. But how do we know it really is both? Well, quantum mechanics' answer is just, well, it's a quantum system and it had both options, and so it will do both. But the question is, how can we catch it in the act? Well, the most obvious seeming thing to do is to try and just measure whether it's decayed. If it's really doing both, we might hope to catch it both being decayed and not decayed at the same time. But the light example shows us why that won't work. If you try and measure this 45-degree light, which is supposed to be horizontal and vertical at the same time, and you try and measure it with, like, let's say, a horizontal filter, then you might hope to see the light both go through and not go through. So if I had a single photon worth of energy, I might detect it doing both of them at the same time. But actually, that's not possible. If you try and measure whether it's horizontal or vertical, it will collapse to just doing one of those. And it will be no different than if it had just been horizontal or vertical, but you didn't know which. The real interesting case comes when, instead of actually trying to catch the quantum state in the act of doing both at the same time, you ask it about something different. Here, instead of trying to measure it in horizontal or vertical, I decided to measure it at 45 degrees. And this is where I saw a different result than if it had been one or the other. And in a similar way, it doesn't make sense to try and catch the atom in both states at the same time by just measuring whether it's decayed or not decayed. That will just collapse the state into one or the other. Instead, you need to do a measurement of something else. And what is that exact something else? Well, for a system like this atom, it's actually quite complicated. I don't know exactly what that measurement would be, but in theory, there is a measurement that you could have done to this atom that would have told you that it was in this state. It importantly wouldn't give you any information about whether it was decayed or not decayed, and that's why it doesn't collapse this superposition. In a similar way, the measurement that worked for the light was one that gave us no information about whether it's horizontal or vertical. So instead of doing a horizontal or vertical measurement, instead we did something that was exactly halfway between them. And that was really important. It was by doing a measurement that was in between, that gave no information about either of those two options, that we were able to find out that this was the state. So that's what you would have had to do with the atom as well. Some insanely clever measurement that would give you no information about whether it's decayed or not, but would tell you whether it was in this state. Now, there's one other thing I want to address about Schrodinger's cat that also kind of annoys me. So the standard interpretation of quantum mechanics says that whenever you measure a state like this and you get a particular result, so for example, if I took this 45-degree light and I measured it in the horizontal direction, the light has now changed. It's no longer in this superposition state. The light that went through has to be aligned with the horizontal direction, so it will become this state. And in a similar way, when you open up the box, you collapse the state to either decayed or not decayed, and therefore the cat into dead or alive. But is that really when the atom should collapse to decayed or not decayed, only at the point where a human being opens the box up? I think that's super arrogant. It seems to suggest that the cat, who is also having a look at this atom and the machinery that is about to kill it, has no bearing on whether a measurement has been done or not. But let's just say that for some reason you don't count the cat as a measurer. You still very much should count the measurement device as something that can collapse a quantum state. So let's say that this is the measuring device, and if the atom decays, then it will release some radiation, and that radiation will be picked up by this machine that will then say the atom has decayed. This is a measurement device, so in the standard interpretation of quantum mechanics, this should collapse the quantum state. It's no longer in this state. Instead, this part has disappeared and it is only decayed. So at this point, there is no more superposition. Now, you might protest that because this machine is not conscious, it can't collapse the superposition. But that is just not true, and we can experimentally verify this as well. We're back again to the state that is both horizontal and vertical at the same time. Now remember, I said that if I was to do a measurement of this state in the horizontal or vertical basis, I have collapsed that state. So for example, if I do a horizontal measurement, then I know that any light that goes through after this must be in this state, not the superposition state. So this is causing a collapse. But what if I built a machine that would randomly decide whether to put a measurement here or not, and it wouldn't show me what it had decided to do? So there would be a veil over this part, and I wouldn't even see the light as it comes out. If my machine had decided to randomly put this filter into here, and I knew about it, then I would know that this state is collapsed. But given that it's random and I had no idea, would putting this filter in here still cause it to collapse, whether or not I knew about it? Well, I can't do this experiment by myself because obviously I don't have the fancy machine to do this, but I absolutely could make one in theory. And people have definitely done experiments just like this, where they don't know whether there's a measurement inside here or not. In the case where a completely mechanical machine without any consciousness whatsoever, in fact, is very simple, decides to put this filter in here, has this caused a collapse or not? Well, if you say it hasn't, because no conscious observer saw the results, then what happens is this state must stay as it is. And so if I was to then do a 45-degree measurement on this state, I know what would happen. Nothing at all. On the other hand, if this filter going in here counts as a measurement, regardless of whether I see it or anyone else sees the result, then what should happen is the light going through has collapsed. And now, if you do this 45-degree measurement, it does, in fact, make a big difference. It's because the new state of the light is this, and we know that about 50% of the light would get cut out in that case. If that measurement was there, whether or not I knew about it, I can tell you that I absolutely would see a difference between whether the machine had put this filter in here or not, whether or not I knew about it or knew about the results. So measurements are measurements, whether they're done by a conscious being or not. And it makes me laugh sometimes when people talk about how you can't collapse a quantum state unless a conscious being looks at it. Because I want to ask them, like, have you ever talked to an experimentalist? Have you ever asked them how difficult it is to keep a quantum state in superposition? When I used to work in quantum computing, this was something that people would be agonizing about. Any object that interacts with this quantum system that you have painstakingly made is very liable to collapse it. If the interaction between your quantum state and that system happens to be somewhat measurement-like, it will collapse your state, whether you like it or not, and whether you saw what happened or not. And so that's why quantum systems have to be super, super isolated to be able to see quantum effects. So yeah, truly, I think that the pop culture interpretation of Schrodinger's cat is so off the mark. If you want to learn more no-nonsense quantum mechanics like this, then you're in luck, because this is a whole series. I'll link to the playlist. And also, if you want a little bit more and you want to actually do problems and learn the maths more rigorously, then this is also a live course, and I'll have some information about that course in the description. But before we wrap this video up, I actually do want to go into a bit more maths, because I want to show why interference happens in quantum mechanics. So we saw that in quantum mechanics, there is a true difference between uncertainty and superposition. But where does it come from? The surprising thing is going to be that it basically boils down to a minus sign. I'll show you. So far we've been talking about this state, which is in a superposition of being vertical and horizontal at the same time. Now, if you've watched the previous two videos, you know I've been very sloppy, and actually there should be a factor in front of both of these. Both of these are a little bit toned down from what they would be. Now remember, the experiment showed that when you have this state and you do a 45-degree measurement, the result is different than if you had just that state and you did a 45-degree measurement, or you had that state and you did a 45-degree measurement. So why is that? To figure it out mathematically, let's look at both of these two states separately, and then we'll add them back together. If we're interested in the 45-degree measurements, then we ought to rewrite these states in that basis. So let's do that. We'll leave that one on square root 2 out the front, and then we'll rewrite this in 45-degree and 135-degree basis. So remember, this is the same as this. To jog your memory about why, let's draw the vectors. So our basis vectors, these pink ones, are 45 degrees and 135 degrees. And the vertical vector is between them. Remember we showed that to get this vector, we just need to add a little bit of both of these, which makes sense because both of these are kind of already pointing upwards, but this one is pointing a little bit to the right, this one a little bit to the left. Those two bits cancel out. Like this one is pulling to the right a little bit, this one's pulling to the left, so that bit cancels out, but they're both pushing up. And so that is what reinforces. So that's why you have a little bit of this vector plus a little bit of that vector equals this one. Now let's focus on this vector. Again, I'll leave the 1 on square root 2 out the front, and we'll figure out what this vector is here. So it's going to be some amount of this vector plus some amount of that vector. So now here's where this gets interesting. This is the vector we're trying to construct from this and this. This one is pointing in the right kind of direction, but this one is pointing entirely in the wrong direction. So we need to negate this vector. Remember, the negative version of it will be 180 degrees away. And now we have two vectors that are roughly in the right direction, this one and the negative of that one. That's why we want a positive amount of this vector and a negative version of this vector. This is the negative sign that is going to change everything. Let's see how. Now we have these two separate states. For each individual one, it is clear that if I just looked at that and I did a 45-degree measurement aligning with this, then the probability of finding this state, so just the up state, in the 45-degree direction is going to be the square of this, which is half. So, in other words, if I have a state which is fully vertical, and I did a 45-degree measurement, I should expect half of the light to go through. On the other hand, if I did a measurement of 135 degrees, I should also expect half to go through. Now here, it's a similar story. If I was going to have light that was horizontal and did a 45-degree measurement, I'd expect half to go through in both cases. This negative does nothing because to get the probability, we have to square this coefficient. But then how is it that we have these two states that individually both have a probability of half of going 45 degrees and half of going 135 degrees? And yet somehow, when we add both of these together, we're going to find that the probability of going 45 degrees is now 1, and the probability of going to 135 degrees is 0. It comes down to this minus sign cancelling out this. Let's see why. So I'm going to add these. First, let's just multiply out these factors, just because they're kind of annoying. Since the square root of 2 times the square root of 2 is equal to a half, all of these are a half. And now let's collect like terms. So here's the really interesting one. These two are going to cancel because this is positive and this one is negative. So I'm going to get rid of them. And then these two are going to reinforce because they're both positive. And the result is this. This light is 45-degree light, and so when you measure with a 45-degree filter, it will all go through. That was probably quite obvious when you were looking at the experiment, but this is how it shakes out mathematically in quantum mechanics. It all comes down to destructive interference and constructive interference. You might have heard of the terms constructive and destructive interference before in the context of quantum mechanics. For example, I did a video about the double slit experiment and how sometimes in some places it will destructively interfere, leaving behind a blank patch, or it will constructively interfere, leaving behind light, which is what makes up the characteristic interference pattern. This interference here is mathematically very, very similar to the phenomena happening in the double slit experiment. It all comes down to how in a superposition of two options, so in the double slit experiment, the two options were going to the left or going to the right. And in this case, it's about the light being in the vertical or horizontal state. The results of this experiment are going to be different whether you have both of these at the same time in superposition or not. And the reason is because there are terms inside of each of these states, like this term and this term, that cancel out because they have opposite signs. And there are terms like this one and this one that reinforce. A very similar thing happens in the double slit experiment with the cancelling out. And so I briefly want to make that connection a little clearer by showing you some stuff from that video. In the video, I did a version of the experiment where you have a hair in the laser beam. The normal way to do the double slit experiment, though, is to shine a laser on two very narrow slits. Then the light that goes through the left or the right. The hair version is pretty much the same. The light goes through one way or the other. But because this is quantum mechanics, the state of the light that went through is both right and left at the same time. Just like with our polarization experiment, let's look at both of these options separately first. To do that experimentally, we'll block one path at a time with a piece of paper. So here we see what happens when we measure just the right state. The light spreads out. And notice that it ends up in all of these spots, including this one. Similarly, if we look at the left state, the light also just spreads out. And again, see that some of the light does fall here. But what about when we remove the paper to let the state be in a superposition of both right and left at the same time? Well, let's see. We'll start with the light in the left state and we'll remove the paper, and now the light just cancels from this spot. So what's going on? It's constructive and destructive interference that causes this interference pattern. To see it, let's look at the individual states of light again. This is what they each look like, because light is a wave. But something odd happens when you add both of them together at the same time. This looks kind of weird, right? To understand what's going on, imagine that you're on a boat at this spot. Then the wave coming from the left and from the right will have their peaks reach you at exactly the same time. They constructively interfere, which means they make each other stronger. Similarly, the negative troughs from both sides will also meet you at the same time, and so they also constructively interfere. On the other hand, if we move our boat to here, the positive peak from one wave hits you exactly when the negative trough from the other wave hits. The peak tries to pull you upward, while the trough tries to pull you down, and so they cancel. This is destructive interference. They cancel each other out because of the opposite signs, which is exactly what we saw in the polarization experiment. Zooming out, we can map out all the spots where we get constructive interference and destructive interference. The double slit pattern comes from the fact that where there is destructive interference, the light has cancelled out, and where there's constructive interference, it's reinforced itself. This interference is the hallmark of superposition. This is how you can actually tell that a state is really doing both things at once. It's no good to just go ahead and directly measure which one of these two things it's doing. Like with the double slit experiment, if you just measured which slit the light goes through, it will just go through one or the other, and you won't have any interference pattern. The point is to do another measurement. So in this case, it was to do the 45-degree measurement. And in the double slit experiment, it was to do the measurement at the back wall. And the point of doing the measurement at the back wall, rather than measuring the two slits, is that that measurement gives you absolutely no information about which path the light took. And that's why you can see those interference effects. All right, so let's summarize what we learned. We learned that a quantum superposition truly is different to just having one of these states or the other, but not knowing which. You can't tell, though, that there is a difference by measuring in that basis. On the other hand, you will get different results when measuring in some other basis because of the phenomena of interference. Okay, thanks for watching, and I'll link to the rest of the videos in this series in the description.